Okay, so we are live on YouTube and I'm going to start the recording as well. Yes, so we are live on YouTube and I'm going to welcome everyone to the Silicon Valley chapter of IEEE Computer Society event. I am the chapter chair, Vishnu Pendyala. Ours is the largest chapter in the Silicon Valley section of IEEE. We have over 3,500 subscribers in our mailing list and a strong following of over 12,300 on Twitter alone. Uh, so today we are fortunate to have a speaker talk on a very hot topic, which is large language models. As we know, large language models have been gained a lot of prominence for more than a year now. So today's talk is on teaching language models how to coordinate. Large language models, despite their astounding reasoning abilities, are not faithful problem solvers. While their abilities are strongly correlated with scale, even humongous models like GPT 3.5 or GPT 4 can become inconsistent reasoners. Recent advances in verbose prompting techniques like chain of thought try to elicit step-by-step decomposition so that the model can solve a sequence of simpler problems to finally reach the goal. Augmenting external tools like web search or calculators has also been proposed to offload deterministic tasks. However, foundational language models learn neither problem decomposition nor tool usage. So in this talk, the speaker will present some interesting solutions towards offloading reasoning subtasks in the case of mathematical problem solving. For instance, how to teach an auxiliary and potentially frugal language model to coordinate with black box solvers, symbolic or language model based to successfully answer mathematical problems. This talk will focus on successfully teaching language models to perform reasoning from non-human feedback and how rewards beyond just the correctness of the final answer are essential for better learning. Tanmay Chakrabarti is today's speaker. He is an associate professor of electrical engineering and an associate faculty member of the Ph.D. School of Artificial Intelligence at Indian Institute of Technology, Delhi. As we all know, IIT Delhi is a premier institution in the world. He leads a laboratory for computational social systems, a research group specializing in natural language processing and computational social science. His current research primarily focuses on empowering frugal language models for improved reasoning, grounding, and prompting, and applying them specifically to two applications: mental health counseling and cyber informatics. Tanmay obtained his Ph.D. in 2015 from IIT Kharagpur as a Google Ph.D. scholar. Subsequently, he worked as a postdoctoral researcher at the University of Maryland, College Park, and as a faculty member at IIIT Delhi. Dr. Chakrabarti has received numerous awards, including the Ramanujan Fellowship, PA Early Career Award, ACL 23 Outstanding Paper Award, IJCAI 23 AI for Good Award, and several faculty awards, gifts from many industries like Facebook, Google, LinkedIn, JP Morgan, and Adobe. He has authored a textbook on social network analysis. He also has a website where we can get more details, Tanmoy Chuck tanmoychak.com. So before I hand it over to Dr. Chakraborty, I wanted to mention that you can post the questions on the QA window. There's a QA window where you can post the questions. Or if you're on YouTube, you can post it in the chat of YouTube. So with that little introduction, I hand over to you, Dr. Chakraborty. Please take it away.
Thanks. Thanks, Dr. Vishnu, for the generous introduction. And I hope I am audible to all of you, and you can also see my screen. So thanks very much for having me here today. This is really a great opportunity to to talk about our research. So in this talk, what I will try to do, I will start off by convincing you that why building larger and larger models as a larger and larger language models as an all-in-one tool, right, to do like all-purpose activities might not be a good idea. Rather than that, we should focus on empowering small language models, tiny language models, right? And we should also, leverage external tools like calculators, web search, web browsers, right? Different types of symbolic interpreters and so on. And we should teach them how to coordinate with each other, for improved performance, right? And in this particular work, we'll particularly focus on mathematical reasoning, which is one of the tough problems for large language models. Okay, this is a joint work with my PhD student, Subhabrata, undergrad student, Jakirat and Gurusa, and Professor Somen Chakraborty from IIT Bombay. And the talk is based on our work recently published in EMNLP 2023 last year, and this year accepted in AAAI 2024. Just few days back, Joy Kirot presented the paper, in AAAI. Okay, so feel free to interrupt me at any point in time if you feel that some of the concepts are not clearly explained, not clearly understood. Okay, so I really do not need to convince you that large language models are basically present everywhere. LLMs are omnipresent, right? We see experts like Jan LeCun, right, writing tweets almost every day about different types of LLMs, right, different capabilities, their abilities, their pitfalls, and so on. We have also witnessed cases where so-called politicians, celebrities, movie actors, they also talk about large language models, right? And in some ways, LLMs, AI, ML research these days, has become a bit more democratic, and that's good. And people like my father, you see on the right side, right, who is actually a technophobic person, doesn't have much idea about technology, smartphone, apps, all these things. He also knows what ChatGPT does, right? So the way this large language models, specifically ChatGPT, penetrated the society, right? It kind of gives us a hint that this is the right time to design right tools for right purposes. Okay, because nowadays people are using LLMs for decision making, for, let's say, for recruitment purposes, for advertisement, for many other purposes. So we need to make these models faithful, unbiased, explainable, so that they can be used properly. Although LLMs are omnipresent, we do not know. It's still a question that whether LLMs are omnipotent or omniscient, right? We researchers, computer scientists, specifically working in NLP and computer vision, we have been trying a lot to prove that LLMs can do anything, right? We have seen cases where simple problems like question answering, paraphrasing, sentiment analysis, summarization, information extractions. These simple problems can easily be solved by large language models. These are simple problems because these problems can also be solved using non-LLM models, right? If you go back to statistical models or traditional models like traditional deep models like RNN, CNN, LSTM, this kind of models, they can also be efficiently used to solve these problems. On the other hand, apparently complicated problems like open domain, natural language understanding, complex reasoning, low resource language processing, creative writing, creative editing, personalization. These problems are still, difficult to solve, and with LLMs also, we haven't seen enough progress, right? So these are apparently complex problems, and in this talk we will specifically focusing we will be specifically focusing on complex reasoning. Okay, and by the term complex reasoning, basically I would like to point to these kind of problems, right? Which is also called arithmetic problems or word problems. Okay, for example, let's say Alex has 3 apples. She gave one to John, others to Bob. Bob gave half to John as well. John then gave half of his apples to Alex. Who has the highest number of apples, right? Apparently this is a, for a human being, this is not a very complex problem. We can easily solve it. But for a large language model which is not tuned for this kind of task, for them this might be a bit complicated problem because of not only because of the problem structure, but also the way it is written, right? I mean, as you see here, right, he gave one to John, others to Bob. So what do we mean by others here, right? In this case, others means 2 apples, right? 1 apple is given to John, other 2 apples are given to Bob, right? So language models need to figure out that essentially you are trying to subtract 1 from 3, right? So this kind of problems apparently looks very simple, but we have seen cases where large language models like GPT-4 oftentimes fail. So let's look at this problem very carefully. Once again, this is a problem, okay, the one that I just mentioned. And if we use Mistral 7 billion, right? Mistral is a very popular large language model specifically for reasoning purposes, right? You see that it not only produced wrong answer, right? But also, if you look at the steps carefully, the steps were also wrong, right? So, so why LLMs are not a good reasoners? Okay, the first reason is that LLMs do not know what computations to perform, what exact computations to perform. For example, if you look at the steps, right? I can think of these steps as kind of chain of thoughts kind of steps. So it started by saying that Bob receives half of what Alex initially had, so he gets 1.5 apples. So Mistral didn't basically understand that here you need to perform a subtraction. Okay, so what exact computation it needs to perform, the model failed to understand that thing miserably. The second problem is that even if it understands, right, what are the computations needed, what are the operations needed, it doesn't know how to perform those operations, how to perform those computations. For example, if you look at this purple text, it is written that then he gives half of his total back to Alex, which is 0.5 apples. So he failed to understand that here half always doesn't mean 1/2, right? Half can also mean something else. For example, here it basically assumed that half means 0.5 apples, right? But in the problem, it is basically said that whatever you have, right? I mean, how many numbers? Let's say you have 4 apples, right? You basically give half of the apples to other person. So it basically means you give 2 apples to the other person. It's not like you give 0.5 apples to the other person. So how to perform these operations is also not clear. So the model rightly understood that it needs to perform a kind of a division, right? Division by 2, but it basically didn't know, what would be the dividend, what would be the divider. Okay. So what are the reasoning requirements? So if you look at the reasoning in general, right, you need to identify what is given to you, right, what is asked to do, right, and then you need to identify the steps, the computational steps, right, the operations that you need to do, and then you essentially need to perform those operations step by step, okay, to reach the answer. Now, if you believe, or if you essentially allow the large language models like, let's say, GPT-4 or any monolithic language models, right, GPT-4 or whatever, Bard or Gemini, or let's say Mistral 70 billion, big language models, to perform all these 3 tasks simultaneously, you will see that this kind of would become some sort of burden to these models to perform these steps sequentially. Part of the reason is that these models are not trained with this kind of tasks, right? These models are mostly trained to predict next words, right? Or let's say mass language modeling, or let's say the models are fine-tuned on certain tasks, but this kind of reasoning task is something that the model may not be aware during its training time. So what is the remedy? So the remedy is that if we can offload some of these requirements to some experts, right, or some, let's say, some external tools, or let's say some tiny language models which are specialized for these tasks, right, and then you teach them how to communicate with each other, how to coordinate with each other, then you may be able to get appropriate answer for these types of questions. Okay, let's say in this mathematical reasoning types of questions, if you, let's say, if you call an external tool like a calculator, right, and we know that that calculator can perform things pretty quickly, right, and pretty accurately, right, then I think you may end up getting a correct answer. Okay, so that's the hypothesis. And if you and of course, the another motivation behind offloading this kind of requirements to external tools is basically came from the idea of society of mind by Minsky, right? Which society of mind by Minsky, who actually said, Minsky. I mean, I think all of you know who is Minsky. Minsky is a famous, AI researcher, basically a founder of the AI lab at Stanford, and he wrote this book called The Society of Mind. And he was asked, to define a mind, define what is mind, right? And he said that a mind is essentially a combination of elements which has the combination of elements which are mindless. Okay, a mind is a combination of elements which are mindless. Okay, the same idea can be applied here, that if you really want to do something wonderful that our mind can do, right, you may need to rely on components or elements, right, which apparently look like mindless or whatever, not that effective, right, and but when they start collaborating with each other, you will see wonders, right? For example, in our case, these tiny language models or external tools like calculators, they can they apparently look like not that efficient, but if you allow them to coordinate, right, they may perform something which maybe the larger model may not be able to perform. Okay, so That is the hypothesis. And to address these problems, we essentially, contributed these two things. We basically taught the model how to break how to break complex problems into simple steps, right? We also taught the model to plan steps, to take the problem in an efficient way. And then in another paper, we essentially asked the model to collaborate with external tools for some complex problem solving, like some sort of mathematical problem solving. Okay, so I'll first discuss the first part of this contribution, which is how to teach small language models to coordinate with large language models, right? As you see in this figure, so what we'll do here, we will ask a complex problem, like the problem that I mentioned, and the problem will be given to a tiny language model, a small language model. The small language model will then interact with some external tool, or it will interact with a large language model, right? And then it will produce some answer. Okay, so the first part of this talk, I will focus on how small language model will coordinate with large language models for arithmetic problem solving. And the second part of the talk, we will discuss how small language model will interact with external tools, right? For again, complex problem solving. Okay, so let's focus on the first part, which basically tells us how to break complex problems into simple steps and how to plan these steps properly, to solve the end task. And we propose the model called DASLAM. It is essentially a decomposition and solution language model. Okay, and how it works is that it essentially decomposes a complex problem into small subproblems, right? And each of the subproblems will be solved one by one, and then we will combine the solution of all the subproblems together and pass it to a large language model for actual problem solving. Okay, so this is the overall idea. So what is the overall idea? Again, this is the picture. So you see here, this is the input to the model. Then we have a decomposer, which decomposes the problem into subproblems. And the decomposer is a small language model, is a tiny language model. And the decomposer will interact with a solver. Solver is a large language model. We assume that this is a black box model. We don't have control on this solver, right? So solver solves something, and then whatever solver solves, whatever answers we receive from solver, that answer may be correct, may be wrong. That answer will be used to fine tune the decomposer again. Okay, so that it produces better decomposition, right? And we basically keep taking feedbacks from solvers, improve decomposers, right, and so on and so forth, some sort of interleaving fashion. And then at the end of the day, we expect that the decomposer, the parameter space of the decomposer will be efficiently tuned so that you perform the problem, you basically perform better, and you get the actual result. Okay, so this is the idea. So now the question is, how do we train the decomposer, right? And what would be the design choice for a solver, and how do we make them interact with each other? How do we make them coordinate with each other? And right, and why this kind of design choice is important, right? Why do we need a decomposer and a solver separately? Why can't a single model act as a decomposer as well as a solver, right? So these are the four reasons. The first reason is that, as I mentioned, all the large language models, these are not a great problem solvers, right? So if you ask them to decompose as well as solve, right, they may be confused. Okay. So rather than that, if we offload some of the task to a decomposer, right, and if we do some sort of plug and play kind of strategy, right, that may help the decomposer interact with the solver. So that is the first advantage. The second advantage is that, of course, if you keep decomposer and solver separate, then not then decomposer will not get affected by solver's performance, right? So you can actually fine tune decomposer separately. Okay. The third advantage is that it will of course help you give more explainability, some sort of modularized structure, and more transparency. And of course, whatever solvers perform, solvers action can determine how you fine tune the decomposer, right? So this is the architecture of Daslam. Okay, it's a bit complicated, but I'll try to explain each of these modules one by one. Assume that this is the question that is asked to you, that is asked to the language model to solve, and this is a complicated arithmetic question, right? And let's assume that the solver is not able to solve this question properly, right? So whatever response the solver model generates, this is wrong. Okay. So what we do then, we ask the decomposer to decompose this complex problem into simple sub-problems. So these are simple steps. These are sub-problems, right? So the decomposer will decompose the large complex problem into small sub-problems. Each of these sub-problems will be given to the solver one by one, right? Solver will produce some response to each of these sub-problems, right? And then at the end, what you do, you essentially concatenate all these question response pairs with the original question and pass it to the solver, and the solver will essentially be able to perform to get the right answer. Okay, so this is the idea. Very simple. Decomposer will decompose the complex problem into sub-problems. Each of the sub-problems will be given to the solver. Solver will solve the sub-problems one by one. Solver may be right, may be wrong, right? And then when we get answers to all the sub-problems, we concatenate them together, and then we basically pass it to the solver, and the solver will be able to solve the question. Okay, the original question. So here, the first question is, how do we design the decomposer, right? How do we fine tune the decomposer? Okay, what would be the design choice of the decomposer? So let us focus on the decomposer, because in our case, solver is a black box model. Solver is a large model like GPT-4 or whatever, GPT 3.5 and so on. But a decomposer is a tiny model. It's a 7 billion model, and in fact, we haven't fine-tuned the entire decomposer. We basically fine-tuned the LoRa adapter. We took an adapter, right, low-rank decomposition, and we only fine-tune the LoRa adapter. Okay, so how do we fine-tune? Now, what is the purpose of the fine-tune? The purpose of the fine-tuning is that the model should be able to to decompose a complex problem into sub-problems. Okay, so your fine-tuning strategy should be such that it would basically let the model learn, given a complex problem, how it can decompose the complex problem into sub-problems. Okay, so this is the our fine-tuning data set. We have so every sample in our data set looks like this. We have a Q gold. Q gold is the original question that we want to solve, right? We have a gold standard reasoning. Now, in the data set, the data set that we essentially used, in the data set, the reasoning steps are also given, right? And then we also know the gold answer, the actual answer of this question, right? And then what we did in order to produce this sub problems corresponding to the problem, we used GPT 3.5 and we converted every reasoning step into a question. Okay, so there are reasoning steps. So we convert every reasoning step to a question. Okay, now for every gold question, we know the sub problems or sub questions, right? We use GPT 3.5 for this conversion, but of course, if you have human annotators, you ask the annotators to annotate these questions, sub questions for a particular question, for a particular gold question. So this is our training set for fine tuning. Okay, so the LoRa fine tuning happens in two stages. In the first stage, is more of a more of a simple instruction fine tuning strategy, where given the question and the and the sub problem and the reasoning steps, the model actually figures out what is going to be the sub problems, right? This is something. So basically, given this and this, the model actually learns how to generate these sub problems, and we essentially did this using a normal instruction fine tuning kind of strategy. Okay, so through this objective function, the model actually learns or gets the ability to decompose a problem into sub problems. But remember, so far the model doesn't know what the solver will respond, right? If the solver responds in an erroneous manner, how to update the decomposer's parameters, right? So it is still blind to the actual error made by the solver language model, right? So in order to cater to this problem, right, we came up with some sort of deterministic reward. Okay, so now these reward functions are based on the solver's response. Okay, again, we have the decomposer, right? Phi. The decomposer decomposes the problem into sub problems. Each of the sub problems is given to the solver. The solver, basically generates the reasoning steps as well as the answer. And based on this answer generated by the solver, we come up with 5 rewards, right? And these rewards are essentially used to further fine-tune the decomposer using policy optimization setup. Okay, so let us first understand these rewards one by one. There are 5 rewards, and these rewards are not a simple reward which checks whether the accuracy, whether the answer is correct or not. It also looks at tiny details of the steps, right? The first reward actually measures that how many entities are being covered by the generated responses and how many entities are there in the original questions, right? So what do I mean by entities? The entities are essentially named entities or numbers. Let's say this is the gold question, right? And we see that, let's say assume that there are 5 named entities, 5 distinct name entities, and these are the responses generated by the model, and in the response there are 9 entities, right? We basically take a ratio of these two. Okay, now closer the number, higher the reward. Okay, so we basically wanted to make sure that the entities which are present in the question should also be present in the responses generated by the model. The first reward. This is the second reward. The second reward is the consistency of answers to sub problems. Okay, so we know that let's assume that ei hat is the entity whose value has been asked asked to predict in the subproblem, and EI is the entity which is there in the gold question to answer, right? Ideally, EI hat and EI should be same, right? So if these two are same, then this is the identity function. It will return 1, right? So we'll also see, right, whether the text generated by the model in the subproblem are similar to the question present in the original question, that the text present in the original question. We simply took a cosine similarity between the subproblems and the answer generated by the model. Okay. For example, as you see here, this is the question, right? This is the answer generated by the model, right? We take the cosine similarity between this and this. Okay, assume that the cosine similarity is this, and in our case, the entity which is being asked to determine, and the entity that is being determined by the model, both of them are same. Therefore, this is 1. So the reward is 1 plus the cosine similarity. Okay. So the third reward is the number of operations, right? So how many number of operations are there in the gold kind of gold reasoning steps, and how many operations are being generated by the model, right? We basically take the ratio of these two. As you see here, this is the model generated response, and there are minus, minus, plus, minus, minus. So there are 5 operations, right? And in the gold steps, there are essentially 1, 2, 3, 4 operations. So we see how many operations are matching. So there are 3 operations which are matching, and therefore the ratio is 3 by 4, right? Again, closer the number, higher the reward value. Okay. The fourth reasoning, the fourth reward is called constructive proximity between generated responses and the initial response. So what is happening is that as we fine tune the model, we expect that the reasoning steps will be better and better, right? And how do we know the reasoning steps will be better and better? We essentially measure the cosine similarity between the gold reasoning steps which are given to us and the steps generated by the model. So it should be like that. It should be like over the iterations, the similarity between gold reasoning and the reasoning generated by the model should be higher than the similarity between the goal reasoning and the initial reasoning produced by the model. Okay, so that is what we wanted to capture here. This is again an example, and of course the final reward is whether the answer matches with the goal answer or not. Okay, if the answer matches, then it will return 1, otherwise 0. Okay, so we essentially combine all the 5 rewards, and remember, these are all deterministic rewards. These are not non-deterministic rewards. Like, so this is not RLHF, by the way. So this deterministic reward is given to the model, and we use a proximal policy optimization technique, PPO technique, to again fine tune the parameters present in the decomposer. Okay, so this is it. Let's look at the results. Okay, so our model is DASLAM, and these are the baselines. These are very recent baselines published in 2023, 2022, like a simple chain of thoughts, least to most prompting, progressive hints prompting, and so on and so forth. So if you look at the performance, DASLAM outperforms all the models, all the baselines. The second observation is that if you look at, now somebody can say that, let's just use the black box model as a decomposer. Why do we need two different models? Why do we need a decomposer and a solver separately? Can we just use the solver for decomposition. Can we think of solver as a decomposer? You prompt the decomposer will generate sub problems, and again you basically give these sub problems to the solver for solving, right? We did that, and this is the result. So we use GPT 3.5 as a decomposer, and you see that it doesn't help much, right? So the third one is right. The third one is a is Daslam minus the feedback, right? One may ask the question that what is the purpose of this reward? Can you remove the reward component? And we showed that if we remove the reward component, again the performance decreases. Okay, and finally, we tested the model on a very complicated data set, which is the JEE benchmark. So JEE, joint entrance examination, is an examination happened in India. This is basically an entrance exam to get into IITs, all the IITs, right? And this this is assumed to be a very difficult exam. So we took JEE benchmark data sets and we asked the models to perform on the JEE benchmark data, right? So we compared our tiny model. Remember, ours is a 7 billion. Our model with GPT-4. GPT-4 has 1 trillion parameters, right? So these yellow lines are GPT-4's results, right? And green lines are our models. As you see that our model is quite competitive, right? Competitive with GPT-4. Many cases, they are similar, accuracy is quite similar, and so on and so forth, right? So this once again, kind of proves that we should rely on tiny models more rather than large models, because large model is something which we can't fine tune. We don't understand the nitty-gritties of these models and so on and so forth. Okay, so this is the first part of the talk. If there is any question, please let me know, Vishnu, if there is any question. Otherwise, I can move to the second part.
There are no questions on the chat window, but I was just curious. Can these solvers be built into the large language models like GPT? Because
yeah, the solver. Yeah.
Huh?
Yeah. Go ahead.
No, they solve a very fundamental problem, right? Of reasoning. So why can't these solvers be included in the functionality of the large language models?
So the solver in our case is a large language model. Okay. In our case, the solver is a large language model, but decomposer is a small language model, right? Solver, if you give this problem to the solver directly, solver will not be able to perform properly because the solver doesn't know how to solve it, right? Rather than this, if you give appropriate steps, right, to the solver should be able to perform it properly. So I mean, this is same as the chain of thoughts prompting, but in our case, we explicitly train a small model to generate this chain of thoughts. In our case, it is basically the decomposer. The decomposer is trained in such a way that it generates the steps properly, and the steps will be given to the solver for solving the problem. The actual task is being done by the solver, which is a large language model. Okay, but the way we coordinate with the solver is something that is important, and we hypothesized that if we coordinate in an appropriate manner by breaking the model, by breaking the problem into sub problems and giving the sub problems to the solver should be able to perform properly.
So does it have to be an external tool, because solver is also a language model, right? So
there is no external tool. So as I mentioned, the first part, so whatever I discussed so far, there was no external tool. There was a small language model and a large language model. Small language model is taught how to coordinate with a large language model. In the second part of the talk, I will essentially tell you how to use external tool for problem solving.
So yeah, can't the small model and the large model be combined? Can't the functionality be implemented together?
What do you mean by combining them? This is also some way combining, right? The way, I mean, our paper, I mean, our Dasla model, it also kind of combines LLMs and small language models kind of interleaving fashion, right? I mean, I didn't get the question properly. Do you want to, I mean, do you mean to say that without decomposition, can we just teach the large language model to solve to solve these problems directly?
Yeah, so can't the large language model be taught to decompose the problem as well?
Yeah, so that is what I showed, right? If a large language model, so this is the result. So this result indicates that, so I use the large language model as a decomposer, right? And this model is also a solver. So GPT 3.5 is acting as a decomposer as well as a solver, right? I can't
But
fine tune GPT 3.5 because, of course, fine tuning is not possible. This is a black box model. I use prompts. I used efficient prompts to basically let the model decompose the problems into subproblems.
yeah, that's right. But the two GPT 3.5 models are separate, right? They're
Separate,
working in
separate.
tandem.
They are separate. Yes,
Yeah,
they are separate.
so maybe it's not possible, but can't the two models be integrated into one?
So integrated means you basically want to say that can only one model perform both decomposition and solving, right?
Yeah, eventually, at least.
I mean, this is what is happening. Look, so when I prompt a model, I'm not updating the model, right? I'm not fine tuning the model. Prompting means I'm just writing some natural language text, right? So you can, so instead of thinking of two different GPT-3, you just assume that there is only one GPT-3, right? In one GPT-3, at first step, I write some prompt and the model produces the responses, right? In the second step, I give these responses to the same GPT, right? And the model basically produces the output. It's the same GPT.
Yeah, that's right. Yeah. Uh,
I'm
If,
not
if
fine
I
tuning it because I don't have access to that.
if I can interject for a moment, it's extremely important to break up the model, the monolith of one model, so that you can see and verify the logic that is executed. That's I think the general point of making separate models is to
Yeah.
see the communication between them. Without
Yes.
that, we can't see it, we cannot progress.
Yes. Absolutely.
yeah, so
Absolutely.
yeah, I got that point, but eventually, at least at some point of time, would it be possible to combine the both the functionalities? Is what I was wondering, but may not be possible because the transformer architecture works in a different way, and uh,
So
yeah,
I haven't understood what you mean by combining. They are already combined, right? GPT 3.5 knows how to decompose. GPT 3.5 knows how to solve, but the way it performs is not appropriate. Therefore, it produces wrong answers. So that's why we said that, it's basically an overburden for a large language models to perform both things together. Rather than that, if we can offload some of these tasks to specific specialized models like a small language model or an external tool, that may help the large language model perform better. That is the hypothesis.
okay. I think there's a question on the chat window also.
Okay.
Have you considered pipeline method for of solving the problem?
Sorry, what's the question?
Have you considered pipeline?
Pipeline means what? Have you considered pipeline methods of solving problems? What does it mean? Ajit, what do you mean by pipeline method of solving the problem? I didn't get it. Nevertheless,
So
I think
maybe,
that,
yeah,
yeah,
I think he is referring to the same thing that we
yeah.
discussed just now.
Okay, okay. Okay, so let me proceed. Okay,
Yeah.
let me proceed. Just a minute. Okay, so now I will discuss how a small language. So far we discussed how a small language model will coordinate with a large language models for better problem solving. Now I will discuss how a small language model will coordinate with an external tool for better problem solving. Okay, so again, the same kind of problem setup. We have a word problem, mathematical arithmetic reasoning problem, and we offload the algorithmic computation to a deterministic solver. So in our case, a deterministic solver can be a calculator. A deterministic solver can be, let's say, a Python interpreter, for example. Okay. So, and then we fine tune the small language model using feedback from the symbolic solvers, from the deterministic solvers, right? So that over the time, over the iterations, the symbolic solver should be able to produce answers properly. Remember, symbolic solver can be a calculator, can be a Python interpreter. We don't have access to their internal process, right? What we can do, we can get, and these are deterministic solvers, right? They are not erroneous. They are not a non-deterministic solver like a large language model. They are deterministic solvers. So we whatever response we get from these solvers, we will fine tune the small language model accordingly, so that eventually the symbolic solver will perform better. Okay, so this is the architecture of the second model. We call it Cyrilum, and what it does, let me again go step by step. So this is the question that is asked. Jason grew 37 watermelon, 30 pumpkins, right? Sandy grew 11 watermelon. How many watermelons did they grow in total? This is the question. Okay. So what our model does, so the input of our model is as follows. We have an instruction. What is the instruction? The instruction is, for the following reasoning question, generate a Python code without importing any library, which solve the question allowing following the instruction. So we first translate the problem into a Python code. Okay, and the input is the problem itself, right? And an additional instruction. The additional instruction can look like this. For example, state the number of variables required in the first line, declare all the variables required as x1, x2, x3, ... Define function solve and pass all the variables as parameters, write the function as required, return the final answer. This is basically the instruction that you are giving to the model, so that your model follows the instruction properly and writes the Python code accordingly. In this case also, we use a small language model, right, and an adapter. Again, the small language model is essentially a 7 billion model, right? And we use a LoRa adapter. We fine tune the LoRa adapter. So what it does, assume that you have a data set where there are mathematical questions, right? You can use GPT 3.5 or whatever, GPT-4, right, to generate Python codes, right? I'm basically telling you how to create the training data set, right? We need a parallel data set where you have the Python code, you have the actual problem, arithmetic problem, and the corresponding Python code, right? So we use GPT-4 to create this data set. So GPT-4 translated the math question into Python codes, right? Some of the Python codes are not executable, so then we essentially included a Python interpreter. In our case, this is SciPy. So we essentially included a Python interpreter, and we ran all the code generated by GPT-4, and we only considered those Python codes which are executable, right? So in our training data set, now we have the mathematical problem and its corresponding Python code which is executable, which produces right answer. Okay, so we use this, and then these additional instructions are handwritten. These instructions are same for all the training data points, right? We use this parallel data to fine tune the adapter, right? And we fine tuned it using a simple language model kind of objective function, where given this as an input, the task is to produce this Python code. Okay. Once the Python code is produced, right? You can use a Python interpreter, right? You can use a Python interpreter, and Python interpreter will generate the answer. Now, the answer may be wrong. If the answer is wrong, we or whatever, if the answer is right or wrong, we take it as a feedback. Okay, in the same way, the way we discussed last time, we take this as a feedback, and this feedback will act as a reward, right? And this reward will again go to the adapter through PPO for further parameter optimization. This is again a deterministic reward. Okay, so what is the difference between the previous architecture and this architecture? In this architecture, there is no large language model. There is a small language model which basically translates a problem into Python code, right? A Python code will then interact with a Python interpreter. The Python interpreter will produce the answer. The answer will be fed to the reward module for further fine tuning. Okay, this is the overall strategy. So we essentially did two different. We performed two different experiments. In one set of experiments, we translated the problem into Python code, and then we employed Python interpreter. In another setup, we translated the problem into algorithmic steps using pseudocodes, right? And then then we employed a calculator to solve that particular problem. So there are the same setup, but two different set of experiments. One experiment, the external tool is a Python interpreter, and we have Python code generated by the small language model. Another case, we have a calculator, and the small language model produces the pseudocode. The pseudocode is given to a calculator. Calculator calculates the answer, and it is given to the small language model for further fine tuning. Okay. Okay. So now let's look at these rewards. There are 4 rewards, right? And these rewards are essentially motivated by the pedagogical, recipe that we generally use to teach school children to teach school children how to solve a problem, a mathematical problem, right? So generally, we essentially follow these 3 steps. The first step is more of reading the problem and allocate variables, right? So whenever a child reads a particular, let's say, math problem, he or she first tries to understand what are the variables, what are the target variable, and so on and so forth. The next step, he or she tries to understand what are the operations needed, right? And how these operations are essentially connected to the variables, what are the constraints, and so on and so forth. And the third step is how to solve this how to solve the actual problem using all these operations and variables, right? So these are the 3 steps. So our reward functions are also motivated by these steps. The first reward is the difference between the number of variables produced by the problem and the goal problem, right? We look at whether the number of variables produced by the model, right, by the small language model is same as the the variables present in the goal data. The second reward is the number of arithmetic operations which are common in both goal problem and the generated problem. The third and fourth rewards are essentially the absolute difference between the answers produced by the model and the goal and the gold answer. And the fourth reward is whether it is a successful Python code or not, whether the Python code can be compiled properly or not, it is executable or not properly. Okay, so these are the rewards, and we sum them up, and we and you see this is a deterministic reward. This is given to the small language model through PPO, and the PPO updates the parameters of the LoRa adapter. Okay, so this is the experimental setup for, as I mentioned earlier, there are 2 setups. In one setup there are in one setup, small language model generates the Python code. In our case, the small language model is a Vicuna 13 billion model, right? The Python code is given to the Python interpreter, and then the rest of the things follow. The second setup, we have GPT-J 6 billion model, which translates a problem into pseudocodes. The pseudocode is given to the calculator for problem solving, and the calculator's output is given to the PPO for further fine tuning. Okay, let's look at the result. So we compared our method with, again, very recent 3 methods, ART, PAL, and TRICE, and we took 3 benchmark datasets: GSM-8K, Math, Arithmetic, and CBM. And if you look at our method outperforms other tool-based methods, right? Now, one may wonder, what is the difference between these and, let's say, tool former? A tool former is a very famous idea, very famous paper, which also says that instead of relying on the large language model, one should think of invoking, tools, external tools, right? But the difference between tool former and our model is that tool former does all these tool invoking steps in silos. What does it mean? It means that whatever output generated by the tools, those outputs are not being fed to the model for further fine tuning, which is happening in our case, right? Tool former actually teaches the model when and how to call the external tool. So you just call the external tool produces something, and you just go on. It doesn't care about whether the external tool produces the right answer or wrong answer, or this answer should be fed into the reward function for further fine tuning. No, right? It only teaches you how to call external tools. So in our case, we hypothesized that instead of just calling them in silos, we should also incorporate the output produced by the tools into the fine tuning stage for better fine tuning. Okay. So as you see in the first case, where the purpose is to generate Python code, better Python code with Vicuna 13 billion. Our model outperforms all the baselines. In the second setup, where we generated pseudocode with GPT-J 7 billion, there also the model outperforms the other baselines, right? One can also say that, can we, instead of doing this, can you also think of some sort of prompting, let's say some sort of k-shot prompting, 1-shot or 4-shot prompting, or some sort of fine tuning, right? Fine tuning the language model without any parameter, without any reward itself, right? And we showed that the reward part is very important, otherwise the performance drops, and prompting doesn't help much in this case. Okay. So now one can also argue that, out of 4 rewards that we defined, right? What are the how are they important, right? It turned out that, let's say, if you drop these rewards in isolation, you drop R4, you drop R3, and so on and so forth. It turned out that R4 is highly important than R3, then R2, and then R1. What is R4? R4 is the absolute difference between the gold answer and the generated answer. R3 is number of variables. R2 is number of arithmetic operations, and R1 is whether it is compilable or not. So if you feel that only taking whether the model produces the right answer or whether the Python code is interpretable or not is enough, this is not enough, right? We also need to look at other factors like the number of variables produced by the model, number of operations produced by the model, and so on and so forth into the reward function. Okay. Okay. So what are the takeaways? The first takeaway is that heterogeneous specialized modules improve model efficiency and robustness of language model-based planning and solution for complex word problems. So at least in the arithmetic reasoning problem, we have seen heterogeneous models like external tools like different types of small language models are very efficient in solving these problems. LLM should not act just a glue, right? For example, if you look at, as I mentioned, into tool former just as a tool former acts as a glue between the large language model and the external tools, and it basically stitches, right, large language models and the external tools in some ways. These two things are not interconnected. There is no interplay. But in our case, we basically taught the model how to interplay, how to interact with each other, how to coordinate with each other for better performance. We also showed that the planar language model, the small language model, need not be very large. Right, in our case, this is basically 7 billion, 13 billion models, and it should be relatively easy to tune, to train, to fine tune, and it should be the planar language model should be task agnostic, right, tool agnostic, right. So these are the major takeaways. And of course, deterministic reward in our case was good enough, right? One can think of complicated RLHF technique, but there is no human feedback, at least in our case. Okay, I'll take 2 more minutes to introduce the lab and the other works happening in the lab. So, so I lead this lab called LCS2, Laboratory for Computational Social Systems. We broadly work in 3 areas. The first area is more of a foundational model, the one that I discussed today, right? So apart from reasoning steps, reasoning abilities, right, we are also looking at so the overall goal of the lab is to design tiny models, right, to empower frugal models as much as possible so that they perform equally good, right, as good as a large language model. So in one of our papers in NeurIPS 2021, we showed how we can efficiently design transformer, right? We basically took an analogy between transformer and multi-particle dynamical systems, right, in physics, particle physics, and we showed that if we think of world, right, in a transformer moving across layers as particle moving across different spatio-temporal regions, right, you can borrow all sorts of ideas from particle physics, like all sorts of ordinary differential equations from particle physics to redesign transformer in a very efficient way that would reduce the parameter space significantly. So we showed, so we proposed a model called TransEvolve, which reduces the parameter space half of the original transformer parameters present in the actual model, right? And the good part is that we will this model also doesn't compromise on the accuracy of the model. We also design models, some sort of multimodal large language models where different modalities can be fused. In our case, the modality was, so one modality was the graph modality, and the other modality was a text modality. We didn't look at speech or image, some other modalities. In ACL 2023, actually, there's a typo. There we looked at prompts, specifically multilingual prompts, and we showed that how multilingual models like MBERT or MT5 or the recent multilingual generative models, they can be used in the cross-lingual setup, right? Let's say you have a lot of training data, you have a lot of examples in English, but you have almost no example in Spanish, or let's say you have no example in Hindi, for example, low resource language. So can we leverage the examples present in English to write prompts in Hindi, right? And this is not a simple translation. So can we think of efficient cross-modal prompting for this? Okay. We also did some work to quantify the creativity of a large language model, quantify hallucination of a large language model, and recently we have started working on model distillation, again with the same purpose, that can we think of leveraging large language models to produce small language model, right? Some sort of model distillation, teacher student kind of setup. Okay. Application wise, we are focusing on two applications. The first one is cyber safety. Cyber safety is cyber security, where we are looking at problems like hate speech, fake news, misinformation, harmful memes, other cyberbullying, right? How we can detect them efficiently, how we can track the spread of this offensive content on social media using graph neural networks and other techniques, right? And another area which I'm very interested in, I'm very passionate about actually, is mental health counseling. So oftentimes we have seen that mental health patients are reluctant to express themselves in front of therapists, right? So also therapists, if you look at the number of therapists across the globe, there are only 10% therapists, 10%. I mean, if you consider 100% patient, there is only 10% therapist present, right? And each therapist takes more than an hour to interact with the patient. So can we think of a better dialogue system which will act in between therapist and the patient? The dialogue system, the dialogue agent will, let's say, interact with the patient before the patient interacting with the doctor. And the dialogue agent will essentially ask questions one by one in an empathetic way, so that the patient express themselves, and then based on the discussion, the model summarizes the counseling note, and the counseling note is given to the doctor for further assessment. So we basically wanted to deploy AI-based models into the counseling system to make the entire process efficient and effective. Okay. And we have done quite a few work on this around this specific area. Okay. So with this, again, I would like to thank ACM, because I think this is a part of, I was invited through ACM speaker. So I'm a distinguished ACM distinguished speaker. So, I would like to acknowledge ACM, one of the largest, one of the largest association in computer science, for connecting me to your society, to Vishnu and the IEEE society. Okay, so yeah, with this again, I will also like to thank all my sponsors. So the project is funded by the direction of research that I mentioned today is funded by IBM, Adobe, and DRDO. So DRDO is a defense agency in India, right? And there are other projects funded by companies like Facebook, Google, LinkedIn. And so we really thank those industries and funding agencies for the generous support. Yeah, I'm open to questions for the discussions.
So thank you, Tanmay. That was really very insightful, and also the research profile is extremely impressive. All the great work that you're doing. So Daniel Peters is raising his hand. So Daniel, can you please unmute yourself and speak up?
Yes, excellent presentation. I think it definitely moves the technology forward. May I make an analogy? I'd like to have you consider if this analogy works. Right now, the big language models are like a very large monolithic spaghetti code of software, and you're bringing forward a modularity idea or paradigm for coding the AI, which allows more understandability and also enhancements of individual models quite separate from the monolith. Is that a good analogy, or is it a flawed analogy?
It's a good analogy, right? And this is the analogy which we used in our research, isn't it? So, I mean, of course, there are ample scopes for improvement. For example, this modulary structure is the modulary structure is something which people are actually, if you look at the current literature, recent literature, the modular LLM is something which people are voting for, right? And the beauty of this modular LLM is that you train different modules of the inter framework separately for separate tasks, right? For example, let's say I mean, again, hypothetically assume that you have not hypothetically, there are experiments actually. Let's say you have a transformer model with 12 layers, transformer large model with 12 layers. You can think of each layer corresponding to each task, right? So you take a pre-trained model, you fine tune every layer separately for a separate task, make them expert, right, for different tasks, and then you use this for inference, right? Let's say for example, let's say there's a task where you need let's say sentiment analysis, named entity recognition, right, some sort of understanding, natural language understanding, right? All these subtasks are needed to solve the final task, right? So what you can do, you can actually train each of these layers for separate tasks, separate subtasks, right? And then you finally think of an end-to-end inference engine, right, that can solve the final task, right? So modular LLM is, I think, something which should be the future, at least for us, like academicians who don't have access to huge GPUs, TPUs, right, data sets. For us, a modular structure is the future.
Thank you very much.
So Tanmay, I was also curious to know if there would be any research into metrics to evaluate factors like reasoning consistency and generalizability.
That's a very good question, and there are papers. In fact, we are working on reasoning consistency and faithfulness, right? So what is consistency? So consistency is let's say you have a large language model and you write prompts in 10 different ways, right? You write prompts in 10 different ways and you get 10 different answers. Okay, so therefore the model is not consistent. So we can quantify the consistency with respect to prompts variation, right? And what is faithfulness? Faithfulness is the accuracy. So the model produces an answer which is not correct. So that means the model is not faithful. Okay, the model can be the model can be consistent. The model can produce same answer multiple times, right, without being inconsistent. But all these answers being produced can be wrong, right? So model can be inconsistent. The model can be inconsistent. The model can be consistent as well as non-faithful, right? The model can be faithful but inconsistent. So these two concepts are different, and we recently submitted a paper to ARR where we quantified what is consistency, what is faithfulness, and can we think of a combined metric which is consistent faithfulness, right? So yeah, so there are works happening around this.
Again, one other question is, do you think explainability and interpretability can be somehow built into the large language models, just like the solvers that you incorporated?
Yeah, so again, this is a very hot area, explainability and interpretability. And there are works happening around the globe. And one of the ways to look at, so people have been looking at different ways. For example, if you think of the entire parameter space as a parametric memory, and you keep, let's say, you keep freezing some of the components and some of the parts of your memory and see how your model performs without that part. People have been trying out all these things, but what I am excited about is a new concept called circuits. Okay, so circuit is a way to to understand the way the large language model performs, right? What is circuit? Circuit is essentially, I mean, you can think of, I mean, you can assume that this is the electrical, electrical engineering circuits where you have nodes which are attentions, or attentions are linked together through some sort of path, right? So recently there is a paper which we showed how you can use this kind of notion of circuit to understand how prompt works, because nobody knows how prompt works, right? We know that, write prompts and model produces fascinating results, but we do not know how it is happening, right? How it is happening in a zero-shot fashion, in a few-shot fashion. So there are probabilistic interpretation, there are mechanistic interpretation. Now, mechanistic interpretation is something that I mentioned, the circuit, the circuit design kind of interpretation. We recently submitted a paper to TMLR where we came up with an idea of again designing circuits to explain chain of thoughts reasoning in large language models. So specifically, let's say when you write a particular prompt, which path of your entire circuit gets activated, right? And can we somehow understand through that path that what are the prompts which are more important, what are the prompts which are less important, and so on and so forth. Which part of your memory is more responsible for multilingual reasoning, which part is responsible for cross-lingual reasoning, for multimodal reasoning, and so on and so forth. Again, this is a very hot area, and yeah, we are also working on this. There are other research labs also working on interpretability, explainability.
Okay, but the approach that you detailed in this talk wouldn't probably be very applicable to build explainability, right?
So explainability can be thought of in two different ways. The first way is, can we explain the underlying mechanism of a large language model, right? This is one way. And second way of thinking explainability is that whatever you perform, can you justify the performance, right? You see, there are two notions. One notion is the model performs something, and you then try to understand how this model performs, right? And the second way, whatever you do, can we have justification of that? Okay, so our is basically the latter one, where we justified that, if it's a reasoning task, then the reasoning steps should look like this, right? Okay, so producing a decent reasoning steps itself is an explainability, right? Now think of a case. So you have an arithmetic problem, and you give it to the model, and the model just produces the answer. Versus you give the problem to the model produces the response, the reasoning steps or the sub problems one by one, and the model also produces the answer. So this, of course, the second one is more explainable, right? But this explanation is more of the way we wanted the model to perform, right? It is not the way to understand how the model performed internally. So the way the one that we discussed today basically addresses that problem, that explainability problem. So I would not say this is, I would rather term this as transferability, not explainability. So the modular structure makes the entire framework more transparent.
Okay. Yeah, I have more questions, but I'll probably save them for later. There's a question on the chat window. Ajit is asking, can you elaborate on why the LLM failed for the first problem about apples?
Okay. That's a very good question. I think I tried explaining that part, but very quickly. So, yeah. Okay. Let's look at the question very carefully. Okay. Alex has 3 apples. She gave 1 apple to John and others to Bob. So currently John has 1 apple and Bob has 2 apples, right? Bob gave half to John. So John again got 1 apple from Bob. So John has 2 apples now and Bob has 1 apple now. John then gave half of his apples to Alex. So it means John gave 1 apple to Alex and John currently has 1 apple. So at the end of the day, we see that both so Alex, John, and Bob, all of them have only one apple. Okay. So what makes this thing, what this makes the entire problem complicated? The complicated part is this half part. Okay. Half means, so you need to understand, the model failed to understand that half, when I talk about half is not 0.5. Half is whatever you have right now, it is half of that. Right? Let's say I have two apples, right? I gave half to you. That means I currently I have one and you have one. But model understood that I gave 0.5 to you. Okay. So if you can explicitly ask the model to elaborate on the steps one by one, right? Through decomposition, we showed through decomposition the same problem. Okay. I don't have slides for that, but the same problem. If we use decomposer, and if you let the model understand how to decompose and how to respond to each of the decomposed subproblems one by one, you see the model performs well. It's a very simple problem, but the way it is phrased, the way it is formed, that seems to be a bit complicated for a large language model.
No, but here, look at the statement that John then gave half of his apples to Alex. He's being very explicit. Whereas Bob gave half to John as well. That is vague.
Yeah.
So your interpretation may not be the same as what they intended. Here, it's up to interpretation, right? The answer may be right. Right?
Well, we took a standard math QA data set. Okay. So we did not curate the data set. We took the standard benchmark school level math QA data set. And this was the question provided in the data set. So I'm assuming that the answer, which basically the answer should be that all of them have equal number of apples. That's what it is written in the answer. Yeah.
That is the thing again. It's debatable.
Well, this is just a dummy example, right? I mean, I can give you multiple such examples where the model failed.
No, but the other question I had about pipelining is, if I were to take this whole problem, solve it piece by piece. That's what I was asking. But rather
what do you mean by piece by piece?
Okay, take this whole question, break it up into stages, and you address stage by stage, rather than taking all the questions, ripping it apart and creating a bunch of questions and solving them concurrently.
No, that's what we are doing.
These are all sequential, right? See, when we talk about mathematics, they're all sequential. And the way we express verbally, we can't say, hey, bracket A plus B, close bracket, right?
Yeah.
That's what I'm getting at. So if I were to do that in a pipeline fact,
So that's what we are doing, right? In our decomposition stage, we are decomposing the complex maths into sequential steps, and then we let the large language model solve each of the steps one by one. That's what we're doing. That's what we are doing, right?
I mean, you may be looking at it like that, but the thing the DSLAM one initially that is forming it.
Yeah, look at this figure, right? So this is the question, and these are the sub-problems, the sub-questions generated by the decomposer, right? And the model is now solving the sub-problems one by one, right? And then finally, remember, this is a kind of a chat interpreter, right? So at the end of the day, so through the inter process, we are training the solver how to solve the complex problem. So when the solver solves all these steps one by one, and then we concatenate these steps together with the original question and feed them together to the solver, and we hope that the solver produces the responses, the reasoning steps properly with the final answer.
Now, where would it take this in this questions that you have parsed, that you created? That the question of half, how do you interpret the interpretation comes in the picture here, right? So that, I mean, this is a discussion that can go on for hours. So I think
No, I think
Really?
the I mean, I think you are stuck at the example that I showed, the Apple
yeah.
example.
No.
But
I'm
you
using
know,
it as an
I think,
example to
yeah,
get to this whole mathematical problem,
yeah,
because that one is
yeah,
simple, right?
yeah,
Yeah.
yeah,
It's not that I'm stuck there. It's just that I'm using that as a
yeah,
thing to.
yeah.
I
I
think
mean,
others
exactly.
have questions
Yeah.
as well, so I think they should get a time as well.
Yeah, I think we used up all the time that Dr. Chakraborty gave us, actually, more than what he allotted initially. So let us thank our speaker. I wanted to share this small token of appreciation. You're able to see the screen, right, Tanmay?
Not yet. Let me. I think I need to. No, I can't see. I see your screen. It says Vishnu has started sharing screen. That's all.
But you're not able to see anything that I'm sharing?
No.
I think you may not share that particular screen.
Yeah, you have to share that particular screen.
Yeah.
Let me do this then.
Okay, now we get it.
Thank you very much. Thank you.
If it was in person, we could have presented you a plaque and stuff like that. But,
Thank you. Thanks.
yeah.
Thanks. Thank you very much for the opportunity.
Yeah, thanks for the very insightful talk. We'll keep in touch.
Sure. Okay.
All right.
Bye.
Have a good day and
Yeah,
good night,
you
everyone.
too.
Yeah, bye.